Hello guys, welcome once more to another live video session here on YouTube. So we are going to be looking at oblique impact, specifically the vectorial approach in solving equations in oblique impact. So this is further maths paper 3 and this is our very first live session on further maths paper 3. So maybe some of you might have done this topic before, maybe some of you haven't yet arrived at the topic. So when explaining, I'll take into consideration that there are some of you here who are still to do the topic. So regardless of the fact that you have done the topic or you haven't yet done the topic, stay till the end. I don't know how long the video is going to be, but once the live session is finished, the video is going to be unavailable. So do well to invite your classmates to join the live session. While the live session is going, if you have any question, the comment section is open for you to ask and you are going to receive a reply from me directly in the comment section. Okay, so if you're joining us for the first time, make sure you like the video, you share the live session with your friends, and you also subscribe to the channel. Remember to turn on your notifications so that when subsequent live sessions are available, you'll be notified to come and follow or to notify yourself. Okay, all right, so let's get back to what I have for you today. So we are going to be looking at the vectorial approach in oblique impact. This is just an approach where the line that is joining the centers of the spheres is neither horizontal nor vertical, but it makes an angle with the horizontal. So in most cases, the line joining the centers of the spheres is always parallel to the vector I. So maybe it is always purely horizontal. In some other cases, the line joining the centers of the spheres is perfectly vertical, that it is parallel to the vector J. But in this case, the line that is joining the centers of the spheres is neither horizontal nor parallel, but makes an angle with the horizontal. So it is parallel to a different vector, maybe ai plus bj, where a and b are all different from 0. So that is the case you are going to be analyzing in this video. Okay, and then at the end we are going to take two GC equations that came under this specific approach. We are going to analyze them together. We solve them till the end. Then I'm going to leave an exercise for you to do. In the comment section, I will leave the WhatsApp group for further maths of Mathematics Academy for Africa, so that you can join the group, and if you have a problem, you can always send your problem to the group. I'm also going to leave my number in case you have personal worries you want to get to me. You get to me, and I'm going to do videos and upload so that everyone benefits, and with that we are going to increase the number of A grades and the number of passes in further maths in June 2025. Alright, so we are going to be looking at analyzing motion when the line of centers of the spheres is parallel to the vector ai plus bj. So I try to outline some steps that we have to follow, okay, so that the video is going to be a little bit shorter. All right, so first thing is that we need to determine a vector that is perpendicular to our vector ai plus bj. So the line joining the centers of the spheres is parallel to the vector ai plus bj, so the line is kind of like this. So a vector that is parallel to ai plus bj is just the ai plus bj itself, or a multiple of it, but we'll just focus on using the ai plus bj. But we now need to find a vector that is perpendicular to ai plus bj. In other words, we need to find a vector that is kind of in this direction, okay, that makes an angle of 90 degrees with ai plus bj. That is a vector we are going to find. So in order to do that, we need to use our basic knowledge on when two vectors are perpendicular to each other. Okay, so if I let the vector perpendicular to ai plus bj to be the vector ci plus dj, okay, where c and d are all real numbers, we know that the dot product of the two vectors should give us 0 because the vectors are perpendicular to each other. So if we do the dot product, we need to multiply the corresponding I and j components, and we add and equate to 0. So we are going to have a times c, okay, we are going to have a times c plus b times d equal to 0. So I'm going to, since I need C and D, I'll either find C in terms of A, B, and D, or I'll find D in terms of A, B, and C. So I decided to find C. So C will give me negative BD divided by A. So my vector U, which was actually CI, okay, because this is now C, CI plus DJ becomes, in the place of C, I just replace it with what I've had, which is negative BD over A, and in place of D, I keep it as D. Now, I'm going to run away from fractions, so I'm going to factorize negative D over A. Once I factorize from the first term, I'll be left with B, and from the second term, I'll be left with negative A. So that once I multiply this with negative A, it takes me back to positive D. Okay, so you realize that this is a constant and this is a vector. So this vector U has so many different values. So, but this vector bi minus aj is just the we can call it the basis, the building blocks of all vectors U. Okay, so this is just a little illustration. If this vector in red is, if this vector in blue is my vector ai plus bj, you realize that there are infinite numbers of vectors that are perpendicular to ai plus bj. So if I just start with a starting point, this red vector, this vector in red here, any other vector that is parallel to this vector in red is automatically perpendicular to the vector in blue. That is why you see there we have a constant that is a scalar multiple of this vector. So in essence, just choose anyone. Okay, either you use this one, or you could even allow the negative sign there. Alright, you're going to have a negative B and positive A. But anyways, in examples you are going to see how to apply, but it's very important that you take down the notes, okay, so that when you're reading by yourself, it is going to help you. Okay, so in general, you realize that a vector that is perpendicular to ai plus bj is a vector bi minus aj. So if I give you a vector 2i plus j, the vector perpendicular to it is going to be I minus 2j. You see, we just have to multiply the I component with negative and attach it to the j component of the new vector, and then we maintain the j component of the original vector in the I components of the new vector. But anyways, you must not cram this. We are going to do an example where we don't have constants, and you see how it plays out. Okay, so this is just a general conclusion that I've made from this little analysis. Okay, now so the first thing, like we said, is to find a vector that is perpendicular to the original vector. This original vector is parallel to the line of centers. In fact, the line joining the centers of the spheres is along the vector v. So we just need to find a vector that is now perpendicular to that vector v. That's the very first thing to do. Now the second thing to do is that we need to find a unit vector in the direction of our vector v. Okay, and the unit vector in the direction of the vector v is just given by the vector v divided by its magnitude. That's the definition. Now the third thing to do is that we need to determine the unit vector in the direction of the vector u. The vector u was a vector that was perpendicular to the vector v. So after finding the unit vector in the direction of the vector v, we now need to find the unit vector in the direction of the vector u, which by definition it is a vector u divided by its magnitude. Now the fourth thing is that we need to determine the components. Very important, we determine the components of the initial velocity. I can call the initial velocity maybe of one sphere UA, but if the two spheres had separate initial velocities, maybe if one was not at rest, okay, you need to find their individual components. Alright, so we are just going to focus here on finding the components of the initial velocity of one of the spheres. I think you can replicate that for the other sphere. So we are going to determine the components of the initial velocity, which is UA, of the spheres that are along the vector u and the vector along the vector v and the vector u. So how do I find the component of the velocity along the vector v? Now that component is called the parallel component, okay, because it is along the vector v, and that component is a constant actually. Alright, it's a component, so it is basically gotten by taking the dot product of that initial velocity with a unit vector in the direction of v. Now, the component along u is a perpendicular component. Why do we say so? We say so because the direction u is perpendicular to the direction v. So the component along u is a perpendicular component with respect to the direction v. Okay, and that component, you now call it y. This is just a variable. This is just a symbol I'm using. You can call it anything, but I just choose to call it y. So I call it y to be equal to, instead we need to take the dot product of the initial velocity and the component and the unit vector in the direction of u. So in general, if I want to find a component of a vector in the direction of another vector, the answer is just the dot product of the vector and the unit vector in the direction. You see, so the component along the vector u is a dot product of the initial velocity and the unit vector in the direction of v, and then the component along the direction u is also the dot product of the initial velocity and the unit vector in the direction of u. Okay, but with respect to v, this u is a perpendicular. Is perpendicular. That is why the component along u is now the perpendicular component, because you are taking reference to v. Again, u is perpendicular to v, so the component along u is a perpendicular component with respect to v. Very important. Okay, the fifth, we have to express that initial velocity of the spheres in terms of the unit vectors u and v. So generally, a vector is given by its component in a direction multiplied by the unit vector in the direction plus another component in a different direction that is perpendicular to the first direction multiplied by the unit vector in that perpendicular direction. Let me just take for example, okay, you see the if I give you the vector 2i plus j, how do I actually analyze what is 2i plus j? So this 2i is the component. This 2i we see here, it's just that there is a missing anyways, this is actually supposed to be 2. Let me just put 2i. Now this 2 we see here is actually the component of the vector 2i plus j in the direction of I. Okay, and then there's an invisible one here. So this one we see here is a component of the vector 2i plus j in the direction of j. Now the direction of j is a direction that is perpendicular to I. Okay, so normally this I here is actually the unit vector. Okay, that is in normal circumstances. If I want to write it, I'm going to write I cap. This one I'm going to write, and then here I'm going to write j cap. Is it okay? I'm going to write I cap, and here I'm going to write j cap. Okay, but the thing is that this I cap is just the vector I divided by its magnitude, and since I is a unit vector, its magnitude is 1. So if I take I divided by the magnitude of I, I'm just going to have I. That's why we see 2i. Even j, if I take j divided by the magnitude of j, the result is just going to give me j. Okay, so basically this is just a little explanation. So every vector is given by its component times the unit vector of the direction where that component is, plus another component which is gotten by, plus another component and in the direction of the unit vector where that component is along, and the second component must, in fact the two directions are supposed to be perpendicular to each other. So this is how we get the velocity in terms of the unit vectors. Okay, the last thing but not the least is that we have to redraw the diagram, which is not compulsory. And when we redraw this diagram, we take into consideration that, okay, my line of centers was originally inclined. So since I've resolved everything, my line of centers is now going to be horizontal. But I'm going to indicate that it is not along the vector I. Okay, I'm going to indicate the vector that is along. So initially, the line of centers is along this vector. But if I successfully resolve everything, I can now put it horizontal just for convenience. So you see that this vector v, this unit vector v here is a unit vector of the direction of v. Okay, that's a line of centers. And then the unit vector u is a unit vector of the direction of u, and u was a direction that was perpendicular to v. Okay, then I start analyzing. Okay, so basically this is just a brief history of the 6 things you have to do before you start solving. So you're doing all of these things before you start solving. They might look lengthy because I'm explaining, but once you take an example, you realize that it is very straight to the point. And further math mechanics is a section of further maths where you need constant application. Okay, and remember that practice makes perfect. Okay, so I also prepared an example for us. All right, so the example says that determine the components of the vector u in a direction that is parallel to I plus j, and also in a direction that is perpendicular to I plus j. So let's start with the direction parallel to I plus j. So I'm going to let I plus j to be the vector v. Okay, like we said, let's go back. If I want to find a component in a direction that is parallel to a vector, I just have to take the velocity. I have to take the vector in question, and I do the dot product with the unit vector of that direction. So in this case, you see that the vector in question is 2i plus 4j. Now the direction is I plus j, so I need to find the unit vector in the direction of I plus j. And like we said, if v is I plus j, the unit vector is the vector v over its magnitude, which is I plus j over the magnitude of I plus j, which is I plus j divided by, now what is the magnitude of I plus j? Just a square root of 1 squared plus 1 squared, right? That's the magnitude of a vector. So this gives us 2, so we are going to have root 2 in the denominator, and if we separate, we are going to have I over root 2 plus j over root 2. Okay, so if we want to find a component of this vector u in the direction that is parallel to I plus j, that is in the direction of I plus j, like we said, we need to take the vector u and we do the dot product with what? We do the dot product with the unit vector that is in the direction of v. So my vector u is 2, 4. Okay, the unit vector, I need to put in the column form. The coefficient of I is 1 over root 2, and the coefficient of j is also 1 over root 2. So we are going to take 2 times 1 over root 2 plus 4 times 1 over root 2, which will give us 6 over root 2, which simplifies to 3 root 2. If you do rationalization just by multiplying top and bottom by root 2, you're going to have 3 root 2 as your answer. So this 3 root 2 is the component of the vector u that is parallel, or that is along the vector I plus j. Okay, now what about the perpendicular component? To find a perpendicular component, we first of all need to find a vector that is perpendicular to I plus j. Okay, so I can let that vector to be alpha. So let alpha equal to ai plus bj be a vector perpendicular to I plus j. So if 2 vectors are perpendicular, their dot product is equal to 0. So I have a, b, with doing the dot product with the I plus j, which is just 1, 1, and equating to 0. So we have a times 1 plus b times 1 equal to 0. So from here, a is equal to negative b. So the vector alpha, which is ai plus bj, replace a with negative b, you are going to have negative bi plus bj. We can factorize b because it's a constant. We are going to have what? Negative I plus j, and we can go ahead to use this vector, or we can decide to factorize negative b instead. We are going to be left with I minus j. We can go ahead to use this vector. This was the same scenario we had when we had to factorize z over a in the first instance. Okay, so any of the vectors you use, you are perfectly correct, and all of you are going to have the same answer at the end of the day. Okay, now since we have found the vector, so this vector I minus j is what I decided to use. Okay, so the vector I minus j is a vector that is perpendicular to this I plus j. So if the unit vector, next thing is that we find the unit vector in the direction of alpha. Sorry, this is alpha. So we need to find the unit vector in the direction of alpha. Okay, because alpha is a direction that is perpendicular to this. If we need to find the component of u that is perpendicular to this, we need to take u dot the unit vector in the direction of alpha, because alpha is a vector that is perpendicular to I plus j. Since you have found the vector already, we need to do its unit vector, which is a vector alpha over its magnitude. This is supposed to be alpha, not a. Sorry for the mistake. So it's a vector alpha divided by its magnitude. And the vector alpha, I decided to use I minus j. Like I said, you could still use negative I plus j. You are perfectly correct. And the magnitude will still give you 1 squared plus negative 1 all squared, which is also root 2. Separating, we have I on root 2 minus j on root 2. So this is the unit vector in the direction of alpha. Alright. Now, what is the component of the vector u in the direction that is perpendicular to I plus j? In the direction perpendicular to I plus j is in the direction of alpha, because alpha is perpendicular to I plus j. So in the direction of alpha, like we said, we take the dot product of the vector u and the unit vector in the direction of alpha. The vector u is 2, 4. The unit vector in the direction of alpha is 1 over root 2, negative 1 over root 2 in the column form. So you are going to have 2 times 1 over root 2 plus 4 times negative 1 over root 2, which will just give us negative 2 over root 2, and by third rationalization, we get negative root 2 as that component. Okay, so having that in mind, we have found a component along the vector perpendicular to I plus j and a component along the direction I plus j itself. Okay, so this is, I also had to maybe try to do a brief vector diagram explaining the whole situation, so that when we start solving problems, it becomes easier for us to analyze. So first of all, we have the vector I plus j. How do I even get this vector I plus j? The coefficient of I is 1, the coefficient of j is 1. So I go to the x-axis, mark 1, y-axis, mark 1, get the point and draw a line passing through the point. It gives me the vector in the direction I plus j. Now, next thing is that we already found a vector that is perpendicular to I plus j, and it was I minus j. Okay, so I minus j is the same thing. The x component is 1 and the y component is negative 1. So we just have something like that. So the angle between these two vectors is 90 degrees. So one is going this way, one is going this way. Okay, now this vector, this vector u, which is 2i plus 4j, how do we get it? We just have to, when x is 2, y is 4, so this is the point. We draw a line passing through the point. Now, this first guy here in blue is a vector, is a component of the vector 2i plus j in the direction of I plus j. Okay, you see it is perfectly in the direction of I plus j, and that component is given by 3 root 2. Alright, so this component here is 3 root 2. Now the next component is a component that is in the direction of I minus j, because if you are in the direction perpendicular to I plus j, it means that you are in the direction of I minus j, because I minus j is perpendicular to I plus j, and you clearly see that this is it down here. Okay, and that component is negative root 2. You clearly see it is below the x-axis, so definitely it is negative. So this is a component along I plus j, and this is a component perpendicular to I plus j, or a component along I minus j, since I minus j is perpendicular to I plus j. So initially, if maybe in the equation the line joining the centers of the spheres is along the vector I plus j, okay, if you want to redraw the diagram, we are going to put it horizontal. That's u cap. No, that's not u. Instead, this is u here. So this is let me just call it v. It's just that I did not give it any name. Okay, yes, it is called v, right? I plus j, so it is v. So I'm going to put it horizontal. Okay, I'm going to put it horizontal, and then now this other guy here, which is a cap, is this I minus j. It is now vertical because it has to be perpendicular. So the component along this man, so this component, let me try to indicate it. The component that is, let's start first of all with the component of 3 root 2. So this 3 root 2 component is a component that is along this man. So this component is along it, okay. and then the next component, actually this vector is supposed to, this vector here is supposed to go down. All right, the vector is actually supposed to go down. Just that I was joined as not really taking into consideration everything since I had to explain. And then the other component is a component that is along the unit vector A, which is -2 pointing downwards. So that is it. So you see, when we draw this way and then we try to analyze it this way, it becomes a little bit clearer. Okay, so this is a basic introduction to what we are going to be analyzing henceforth. So from here, we are going directly to past GCE questions. We try to analyze problems on this type of situations where we are going to be applying the Newton's law of restitution and the principle of conservation of linear momentum. Okay, so let's go there. Okay, so like I said, we are moving on to practice exercises. So this is June 2015 paper 3. I can't remember the question, but you can check your pamphlet to know the question number. So the question reads, a smooth sphere S moving with velocity 2 lambda into 2i+j meters per second, where lambda is a positive constant, collides obliquely, that's why it's oblique impact, collide obliquely with an identical sphere T. Identical means they have the same mass, okay, with an identical sphere T which is at rest. Okay, after impact, sphere T starts to move in the direction of the vector 3i plus 4j. The coefficient of restitution between the two spheres is half. State the direction of impulse exerted by S on T. Show that if theta is the inclination of the direction of motion of sphere S to the line of impulses, then the cosine of theta is equal to 2 on root 5. Find the velocity of sphere T immediately after impact. Okay, so we are going to solve it before moving to June 2017. So let me just shift June 2017 downwards. Okay, let me just shift it downwards so that we focus on June 2015 first. Okay, so the first thing we do is we have to analyze the problem. We have a sphere S which is moving with this velocity, colliding obliquely with an identical sphere T which is at rest. So its initial velocity is 0i plus 0j meters per second. Now, after impact, sphere T starts to move in the direction of the vector 3i plus 4j. The question of restitution has been given to us. First question, state the direction of impulse exerted by S on T. So we have to come back to this case. After impact, sphere T starts to move in the direction of this vector. Okay, so it means that the line that is joining the centers of the spheres after impact is along the vector 3i plus 4j. So automatically it becomes the line that is joining the centers of the spheres before impact, because the line joining the center of the spheres cannot change. Okay, so the line joining the center of the spheres remains constant throughout the collision. So it means that the direction of impulse is actually the direction 3i plus 4j. Direction here is vector. It's a vector. So the direction, so the answer is in bold. The direction of impulse, is, or let me say the impulse, let me put the impulse is in the direction of the vector. The vector is 3i plus 4j. So the impulse is in the direction of this vector. This is basically because after impact, sphere T starts to move in the direction of this vector. So if you are moving in the direction of this vector after impact, it therefore means that before impact you were also moving in the direction of that vector. Okay, because the line joining the centers of the spheres doesn't change, it remains constant throughout the motion. Okay, let's go to second part of the equation. Show that if theta is the inclination of the direction of motion of sphere S to the line of impulses. The line of impulses is definitely the line joining the centers of the spheres. Okay, then cos theta is equal to 2 on root 5. So we have to draw the diagram to know exactly what is happening. So since I've already drawn some things here, I'm just going to copy and paste so that we save time. Okay, So analyzing, realize that initially, okay, so initially I'm just going to draw everything. Here's a line drawing the center of the spheres. So let me try to make this one to be a little bit longer. So these are my spheres initially. So initially that's a vector 3i plus 4j. Okay, this 3i plus 4j. This is a line, the line of impulse, or the line joining the centers of the spheres. That's a line. So initially what is happening is that sphere S is moving with this velocity, okay, and sphere T is at rest. So what I do is that I want to first of all draw the diagram. Okay, so this is sphere S. Okay, if it is moving with a velocity of 2 lambda into 2i plus j, anyways, it means that it's kind of moving like this. Okay, because we need to find the components of its velocity along the line of centers and perpendicular to the line of centers. All right, so this is the direction of motion of sphere S. Now next thing is that we need to find a component that is perpendicular to the line of centers. Okay, component perpendicular to the line of centers, and then also a component parallel to the line of centers, that is a component along the line of centers. So we need to find a component that is also along the line of centers, this component. Now sphere T is normally at rest, so since sphere T is at rest, it means that its initial velocity is 0i plus 0j, so there's no need to even indicate. Okay, so this is before impact. All right, so let me just try to indicate this one with us. Okay, so that you know that this us is actually the initial velocity of sphere S. Okay, all right. Now next thing is that after impact, so this is it after impact. Okay, so after impact, normally we also have to indicate at impact, but it's not really necessary. Let's focus first over here. So after impact, sphere S moves in a different direction. Okay, so sphere S also kind of, you have something like this for sphere S. So sphere S acquires a final velocity. So sphere S acquires a final velocity of, let's say, Vs. Okay, so small Vs. So sphere S acquires a final velocity of Vs, and it also has two components. We need to find a component perpendicular to the line of centers and a component along the line of centers. Okay, but this time around sphere T has a change in the component. So sphere T will now have a new component along the line of centers, because during collision, only the component along the line of centers changes, because motion occurs along the line of centers. Okay, so sphere T, initially its component was 0, so finally the component is going to change from 0 to a new component. You can just call it maybe since it is, let's just call it Vt. Okay, Vt. So this Vt here is a component along the line of centers. That is the only component that will exist, because the vertical component was initially 0, so it stays like that. Okay, now we can say that we can just attribute some, we can say that, okay, the final velocity of sphere S along the line of centers is maybe x, so the component along this line of centers is x. Okay, we need to find it, and then initially it is maybe let us say a. All right, so initially it is a, that is the component along the line of centers is a, and the component along the line of centers after impact is x. Now let us say the component along the line of centers finally, that is the component perpendicular to the line of centers is y. Okay, that's after impact, and then initially it is still y, because that component does not change. All right, so this component perpendicular to the line of centers does not change. What is changing is the component along the line of centers. So you see a changes to x. This Vt initially was 0, that's why it changes from 0 to Vt. the perpendicular component was also 0. That is why there's no need to even indicate. So V will also be moving perfectly, T will also be moving perfectly along the line of centers of the spheres. Okay, so this is just a brief summary of what is actually happening. But the question said that if theta is the inclination, which is like an angle of the direction of motion of S, where is the direction of motion of S after impact? This is the direction of motion of S after impact. Okay, this direction here is actually the direction of motion of S after impact. So theta is the angle that direction is making with the line of impulses. So what does this mean? This means that the angle between Vs and this line of centers is theta. So let me just try to indicate, let me just try to put the theta there so that I actually see where the theta is. So theta is actually this angle that is here, okay, the angle between the line of impulses and the direction of motion of sphere S after impact. Okay, so that is the theta that is there, and if theta is here, we can actually resolve this Vs into two components. This component X will be in terms of Vs and the component Y will also be in terms of Vs, but for now let's just allow the component as X and Y. When we have gotten X and Y, we now have to resolve and relate it with theta. Okay, now this is the diagram. Okay, so we have not yet started the equation. I will just here drawing the diagram to really explain so that you understand what is actually happening. So the next thing we do is that we have to apply the Newton's law of restitution and the law of conservation of linear momentum. But before doing that, we must find these missing terms, this A, this Y, this X, and this Y. All right? No, sorry, we must find A and Y. When we apply the law, we are going to find X and Vt. Okay, because Y remains unchanged. So we need to find A. What is A? A is the component of the initial velocity of sphere S along the line of centers. So if we go back to our explanation, I'm going to go back to the steps. Okay, what was the first step? Determine a vector perpendicular to ai plus bj. So let's go and do that. So first I need to determine a vector that is perpendicular to 3i plus 4j. So like we said, we are going to let the vector, let me call the vector alpha. Okay, let alpha, oh, I have to put it in bold. Let alpha equal to, let us say ci plus dj be perpendicular to 3i plus 4j. So my vector perpendicular to 3i plus 4j is a vector ci plus dj. What does this mean? This means that if I do the dot product of the vector ci plus dj with the vector 3i plus 4j, I must get 0. Okay, so let us just simplify. So this means that 3c plus 4d is equal to 0. So I'm going to find one quantity in terms of the other. So what will be c? Negative 4d divided by 3. Okay, therefore we realize that my vector alpha will be equal to, now since alpha was ci plus dj, is going to be negative 4d over 3i plus dj. Okay, so we can just factorize, factorize negative 4 on 3, we'll be left with let's factorize not negative 4 on 3, negative d on 3. Yes, negative d on 3. We are going to left here with 4i minus 3j. Perfect. So you are going to left with 4i minus 3j, because if you multiply this with 4, what do we have? Negative 4d on 3. Multiply negative d on 3 with negative 3, you have positive d. So we are now going to take this vector. So the vector 4i minus 3j is going to be one of the vectors perpendicular to our original direction. Okay, so we are going to choose the vector alpha. So we are going to choose alpha to be equal to 4i minus 3j. Hope you guys are really getting what I'm doing. So with this, I have already found the vector. But in the question, if the vector perpendicular was given to you already, you write on with it. But when it's not given to you, you have to find it. So we have found a vector that is perpendicular to 3i plus 4j. That's a vector perpendicular to my original direction. Okay. Now, let's go back. What's the next thing to do? I want us to take it step by step. Determine the unit vector in the direction of ai plus bj. So we need to determine the unit vector in the direction of 3i plus 4j. So unit vector in the direction. Unit vector in the direction of 3i plus 4j. Okay. What is that unit vector? We said that, let's just call maybe that unit vector to be, in fact, let us say this 3i plus 4j is a vector v. I think we have not used any v anywhere. No, there's a vs. No, let's call it, can I say beta? Yes, let me just call it beta, okay. So my vector beta is 3i plus 4j. My vector alpha is a vector perpendicular to it. Good. So I need to find the unit vector in the direction of beta. And like we said, what is that unit vector? That unit vector is just beta cap, which is beta over the magnitude of beta. So beta cap is equal to beta over the magnitude of beta. Okay. So what is beta? Beta is 3i plus 4j, so 3i plus 4j is beta. What is the magnitude of 3i plus 4j? It's going to give us the square root of 3 squared plus 4 squared, and here we have 3i plus 4j. Now the square root of 3 squared plus 4 squared is the square root of 9 plus 16, which is root 25, which is 5. So you're going to have equal to 3 divided by 5 plus 4 divided by 5. So 3 on 5i plus 4 on 5j. So this is the unit vector in the direction of beta. What's the next thing? I think I can remember the unit vector in the direction of alpha, because alpha is perpendicular to beta. So the unit vector in the direction of alpha, what is alpha? Alpha is 4i minus 3j. Okay. So that unit vector is alpha cap, alright, alpha cap, which is equal to alpha divided by the magnitude of alpha. So my alpha is this, the magnitude of alpha. I'm going to have the square root of 4 squared plus negative 3 squared, and then I have alpha in the numerator. I still have 16 plus 9, 25, square root is 5, so I have 4 on 5 I have equal to 4 on 5i minus 3 on 5j. Good. So I've gotten the unit vector in the direction of beta and the unit vector in the direction of alpha. Okay. Now what's the next thing to do? Let me run and check again. So I think we have arrived. Now let us find the components of the initial velocity of every sphere in the direction of v and in the direction of u. Okay, and we said that the component in any direction is the dot product of that velocity and the unit vector in that direction. Okay, so let's now apply that knowledge. So let us find components of us. Remember that the initial velocity of s is us. So component of us in the direction of, let's begin with beta. Okay, that component, according to what we have replaced in the diagram, the component is a. Clearly the component is a, right? Because a is in the direction of what? 3i plus 4j. So we are just going to proceed. A is equal to, we said we need to take us, okay, and then we do the dot product with the unit vector in the direction of beta, which is just b cap. Okay, so this is going to give me what is US? Now let's go back to the equation. US is 2 lambda into 2I plus j. So if you expand, we have 4 lambda I plus 2 lambda j. We just need the components. So we are going to have 4 lambda and 2 lambda. Okay, we have to do dots. What is the unit vector in the direction here? 3 on 5, 4 on 5. So we have 3 on 5, 4 on 5. So we are going to take 4 lambda, we multiply it with 3 on 5, then we add it, so we take 2 lambda and we multiply it with 4 on 5. So this just gives us 12 on 5 plus 8 on 5, which gives us what? 20 on 5 lambda. And 20 on 5 lambda is equal to 4 lambda. What a coincidence. Okay, so this A is actually equal to 4 lambda. Okay, so I can go to my diagram and replace A with 4 lambda. Alright, so I replace A with 4 lambda. So that component A there is 4 lambda. Okay, now we need to find the component that is perpendicular. So the component of US in the direction of alpha, because alpha was that vector perpendicular to beta. So in the direction of alpha, that is a perpendicular component. So according to the diagram, we said that perpendicular component is y. Okay, that perpendicular component is y. So y will be equal to, by definition, you need to take US dot the unit vector in the direction of alpha, which is alpha cap. Okay, so what do we have? So we are going to have US 4 lambda, 2 lambda, and then we do the dot product with alpha cap, which is 4 on 5 and negative 3 on 5. So 4 on 5 and negative 3 on 5. I'll just copy this and edit. Okay, so 4 on 5, so this is 4 on 5, and then negative 3 on 5. So if we do it normally, we are going to have 4 lambda, we multiply with 4 on 5, then minus 2 lambda, okay, we multiply with 3 on 5. So what do we have? We have here 16 on 5 minus 6 on 5, that's 10 on 5, which is 2 on 5. So 2 lambda is our answer. So this is actually y. Okay, perfect. Now let us try to do a little gymnastics to know if we are actually correct. So if I actually ask you, what is a vector US with respect to my reference frame, you tell me that the vector US, we need to take the component along B, so along beta. So like I said in the last step, we said we have to express, so it is A times beta cap. Okay, we said A times beta cap plus y times alpha cap. Okay, let me go back to that so that you remember. So we had something like this. We have something like express the initial velocity of the spheres in terms of the unit vectors. So this is it. This was a component along the line of centers. This was a component perpendicular to the line of centers. So along the line of centers, the unit vector was v cap. Perpendicular, the unit vector was u cap. So we have to take the component along the line of centers times the unit vector along the line of centers plus a component perpendicular to the line of centers times the unit vector perpendicular to the line of centers. So this is basically what we have done here. Okay, what I've done is I've taken A is a component along the line of centers, and beta cap is the component parallel to the line of centers, that is along the line of centers. Y is a component perpendicular to the line of centers, and alpha cap is that component perpendicular to the line of centers. Let us just verify if we are actually going to have the original vector u. So what do? We need to take what is A. Our A is 4 lambda. Okay, so I'm just going to copy and replace. So my A is 4 lambda. I'm going to multiply it with what is beta cap. Where is my beta? My beta cap is 3i. So this is my beta cap. Okay, so I'm just going to replace it there. then plus what is y? Y is 2 lambda. You multiply with alpha cap. What is alpha cap? Alpha cap is this. Then we try to bring like terms together. If it gives us the original vector us, it means that we are perfectly correct and we can move on. So this is not actually part of the solution, but I'm taking my time to explain so that you actually get what is happening. So the coefficients of I, okay, let me bring the I terms together. I'm here, this is 4 times 3 with 12. So I have, in fact, lambda is common all through, so I can just put lambda outside. Okay, I'm going to have here 12 on 5, 12 on 5. Now 2 times 4 is 8, 12 on 5 plus 8 on 5. Okay, then let's go to the j component. Lambda is also common, then we have j into. Now we are going to have 4 times 4, we have 16, so 16 on 5. Then there is a minus here, but there is a 2, so you have 6, 2 times 3 is 6, so minus 6 on 5. So don't we see that this answer will actually give us, you see that lambda is common in the two terms, okay? We have a common lambda. Now when this lambda is common, what is left here? This is 20 on 5, which is 4, so we have 4i. Now this is 10 on 5, which is 2, plus 2j. Once we factorize 2 from 4, we have 2. Factorize 2 from 2, we have 1. Then we keep the 2 outside. So you realize that this final answer still gives us the answer of the initial velocity. Okay, so this means that those components you have had are the correct components. Voila. So let's now proceed with our solution. So this is not actually part of the solution, okay? This is not actually part of the solution, so I'm going to put it in red. So when we have found all those our components, and let's go to our diagram and indicate this y here is actually 2 lambda, okay? Because we have found it already. So 2 lambda for y. So y is 2 lambda. So this y that is here is 2 lambda. Okay, so I think from here now we have successfully gotten those components, because that's the most tedious part, to get those components. After getting these components, directly to the application of the laws we know, the principle of conservation of linear momentum and Newton's law of restitution. So if you don't know those laws, I'm going to state them, then we apply together. Okay, so first we are going to apply the principle of conservation of linear momentum. So applying the principle of conservation of linear momentum along the line joining, I'm very specific, along the line joining the centers of the spheres. So that principle says that momentum before collision equals to momentum after collision along a given axis. So we don't just apply it, we must specify the axis. Okay, so what is momentum before collision? So I think we'll need to copy this diagram and paste there. We'll need to, let me try to group everything so that I just shift the diagram down. Okay, then we just start using the diagram. I think that is going to save us a lot of have I copied everything? Okay, no, I'm still left with US, VT, and then with the angle theta. Okay, so I think we are good to go. Voila. So I just want to shift this diagram down, okay, so that we just use the diagram directly than to copy and paste it. It's going to be a little bit longer. So I've not actually redrawn the diagram, okay, so I'm just going to explain. Like I said, you either redraw the diagram to suit you, or if you have understood the way it is like this, then fine, we can move on. Okay, so application of the law of conservation of linear momentum along the line of centers. Now what was the mass of the sphere? It was not given, so we are just going to say the mass is m. Okay, they are identical, so they have the same masses, so it does not really disturb our solution. So this law says that momentum before collision equal to momentum after collision applied along the line of centers. That's along the line joining the centers of the spheres. So what is momentum? Is a product of the mass and the velocity. So you are going to take the momentum before collision will be the momentum of sphere S plus the momentum of sphere T. Momentum of sphere S is the mass of S, which is m, as I have supposed, times the initial velocity of sphere S along the line of centers. Okay, what is the initial velocity of sphere S along the line of centers? The component is 4 lambda. Okay, so we are going to have 4 lambda. Are you guys now seeing why we are actually taking along the line of centers? So that's why we need this component along the line of centers, 4 lambda. Now let's go to sphere T. We have the mass of sphere T, which is also S, which is also m, because S and T are identical. Its initial velocity along the line of centers is 0, because initially it was at rest, equal to the mass of sphere S times its final velocity along the line of centers. That component is x. Okay, that component is x, so I have m times x. That is why I'm saying that we are applying this law along the line of centers. So all the components you are taking are the components that lie along that line, plus the mass of T is m, and its final velocity along the line of centers is Vt. Okay, then we equate it. No, I think this is all. So this is the initial momentum, this is the final momentum. So you realize that the masses can cancel, and when the masses cancel, the left hand side will be left with 4 lambda, the right hand side will be left with x plus Vt. X plus Vt. So we can call this man equation 1. So that is our first equation. Now the next thing is that we are going to apply Newton's law of restitution along the line of centers. So applying Newton's law of restitution along the line of centers. Applying Newton's law of restitution along the line of centers, what do we have? So if you apply Newton's law of restitution along the line of centers, we are going to state the law, then apply. So the law says that the coefficient of restitution between the spheres, which is E, is equal to, I think we can just go to the next page. The coefficient of restitution between the spheres E is equal to velocity of the difference of the velocity of separation. Velocity of separation, the difference of that means we need to subtract their final velocities along the line of centers. So I'm going to take Vt minus x, okay, because those are the velocity along the line of centers. Vt minus x. Then I'll divide by the difference of the velocity of approach. Approach means I subtract their initial velocities along the line of centers. But if I began with Vt in the numerator, that is, if I began with sphere T in the numerator, I'll start there with sphere S in the denominator. Okay, so I'm going to take 4 lambda minus 0. But if I began with x, I'm going to take 0 here. I'm going to begin, if I began with S, I'm going to begin here with T. But since I began with T, I'm going to begin with S. So the numerator has final velocities, the denominator has initial velocities along the line of centers, specified again. That's why I'm taking 4 lambda minus 0. But here I'm taking Vt minus x, because those are the guys that are along the line of centers, the line joining the centers of the spheres. Okay, so, but according to the question, what is the value of the coefficient of restitution? I've forgotten. The coefficient of restitution is half. So I'm just going to replace E with half. Okay, so this means that I'll multiply 4 lambda on both sides. I will have 4 lambda multiplied by half equal to Vt minus x. So from here I can have a second equation. So I have 2 lambda equal to Vt minus x. This is equation 2. Then I'm going to solve the two equations simultaneously. Okay, so I'm going to solve this equation and the second equation simultaneously. I think you guys are seeing these two equations. So I'm going to find Vt and Vx. Okay, so let us begin with Vx. Let us begin with x. Sorry, if we subtract the two equations, if I take equation 1 minus equation 2, what do I have? 4 lambda minus 2 lambda is 2 lambda. So I have 2 lambda is equal to, now let me start with the Vt. Vt minus Vt 0. Now let's go to x. X minus negative x is 2x. So we have that 2 lambda is equal to 2x. If 2 lambda is equal to 2x, what is the value of x? So x is equal to lambda. So we have gotten x. Now let's get Vt. So I'm going to take equation 1 plus equation 2. If I add the two equations, 4 lambda plus 2 lambda is 6 lambda. So we have 6 lambda to be equal to, now x plus negative x is 0. Now Vt plus Vt is 2Vt equal to 2Vt. So from here, what will be Vt? Vt will give me 3 lambda. So I've successfully found Vx. I've successfully found Vt and x. Okay, now this question has an aim. What is the aim of the question? We have to prove that if theta is the angle of inclination of the direction of motion of sphere S to the line of impulses, that is after impact, okay, that is after impact, then cos theta is equal to 2 divided by root 5. So come to the diagram, check out where theta is. This is theta. Okay, this is my theta. Now I can express this Vs, because this Vs is actually the final velocity of my sphere, okay, of sphere S, where the components are x and 2 lambda. So in this reference frame, you realize that if I try to create a right angle triangle so that you see perfectly, if I create a little right angle triangle here, right, you see this right angle triangle, right? If I create a right angle triangle there, you realize that if I take tan theta, okay, tan theta is going to give me opposite is 2 lambda. The opposite is this side, which is the same as this side, okay, 2 lambda divided by adjacent, which is x. So tan theta is equal to 2 lambda over x. That's tan theta. So I'm going to remove that. So that's why I needed to find x. So tan theta is equal to 2 lambda divided by x, which is 2 lambda divided by what is x? Our x is lambda. So we just have 2. So tan theta is equal to 2. In fact, we can write it as 2 over 1. Okay. Now, we know that since theta is an acute angle, okay, this tan theta equal to 2 is like, okay, opposite divided by adjacent. Now, you know that since that's a right angle triangle, the hypotenuse squared is equal to the opposite squared plus the adjacent squared, which means that, let us find the hypotenuse. The hypotenuse will be equal to the square root of the opposite squared, 2 squared, plus the adjacent squared, 1 squared. This gives us a square root of 5, right? Okay. So what is cos theta? Cos theta is what? Adjacent over hypotenuse. Okay. What is the adjacent from this diagram? From this diagram, the adjacent, wait, cos is adjacent or hypotenuse? Yes. The adjacent is giving us 1, and the hypotenuse is giving us root 5. So the result is 1 over root 5. I don't know why if I made a mistake somewhere, because our x is actually equal to lambda. So tan theta, let's check again. Tan theta is opposite on adjacent, right? So 2 lambda over lambda. That gives us 2 over 1. So cos is adjacent. Adjacent is okay, wait. Yes, cos theta is adjacent on hypotenuse. Okay, adjacent on hypotenuse. So you are going to have cos theta to be 1 over root 5. But the proof says that we should prove that cos theta is equal to, where is it? Prove that cos theta is equal to 2 over root 5. So I don't know if we have made an error somewhere. And we have not seen. I don't know. Or just give me a minute. Let me check if that question is actually correctly written, because I might have made a mistake when typing the question. So June 2015. Let me check. Kaolu. June 2015. Yeah, it is okay. The question is okay. Cos theta equal to 2 over root 5. Wait. Let us come back here. Wait. Let us see. It is like, let's read back the question. Show that if theta is the inclination of the direction of motion of sphere S to the line of impulses. Okay. Actually, this theta is not after impact, it is before impact. Okay, because according to the equation, the direction of motion is actually the initial direction. So this theta is sorry for the error. This theta is supposed to be here. Okay, this theta is supposed to be here. Okay, theta is supposed to be there. After impact, we can maybe call the angle alpha. Yes. Sorry for not interpreting the equation rightly. So maybe you can call this one alpha. So it is cos alpha that is. So let me just change all of these things. Okay. So here is supposed to be alpha, though we don't really need it, but I'm just going to put it there, and it's supposed to be alpha. Good. Now let us focus on theta. Yes, let's focus on theta. So again, we see that what will be tan theta here? Tan theta will be equal to opposite over adjacent. Opposite is 2 lambda, adjacent is 4 lambda. So let me just do it again. Here, tan theta. So guys, if they have not told you that that angle theta is after impact, know that the angle is before impact. Okay, because I've checked the equation and it does not tell us that it is after impact, it is actually before impact. So I'm sorry for that. So tan theta is equal to opposite over adjacent, which is the opposite is 2 lambda, before impact is 2 lambda, and the adjacent is 4 lambda. Okay, wonderful. Opposite is 2 lambda, adjacent is 4 lambda. So this is going to simplify to give us 1 over 2. So this is again opposite over adjacent. Now Pythagorean theorem says that hypotenuse squared is equal to opposite squared plus adjacent squared. So you are going to have 1 squared plus 2 squared, which is equal to 5. Therefore, what is the hypotenuse? The hypotenuse is the square root of 5, which implies that what is cos theta? Cos theta is equal to, we know it is adjacent over hypotenuse. What is the adjacent? Voila, the adjacent is 2. Okay, so we have 2 over the hypotenuse is root 5. So we have proven that cos theta is equal to 2 over root 5. Good. Now, second question. Find the velocity of sphere T immediately after impact. Okay, so what is the velocity of sphere T immediately after impact? It is just Vt. Okay, because normally velocity of sphere T, the velocity, not the component of the velocity. Let's be careful. So the velocity of sphere T immediately after impact, let me say capital Vt. Okay, because this small Vt was a component. So capital Vt is a velocity of sphere T after impact. What do we say it is? We need to take the component, which is small Vt, in the direction of beta. Okay, accordingly, we take the component in the direction of 3i plus 4g, and we multiply it plus the component in the direction of the perpendicular and we multiply. But since in the perpendicular it is just 0, there's no need. So so we are going to put beta cap. Yes, we are going to put beta cap there. Okay, so that velocity is going to be the component along beta times beta cap, the unit vector. Now the component along beta, we saw already that the answer is, where is it? The answer is 3 lambda. Okay, so we have 3 lambda. The answer is 3 lambda. So we have 3 lambda. We have 3 lambda. Then we need to multiply the result with beta cap. What is beta cap? We come back and just replace everything. Our beta cap, where is it? Here is it. This is our beta cap. So clearly you see that it's in terms of a vector. So just find that is the velocity. So you have to put meters per second. Now, if they ask you to find, okay, what is the velocity of sphere S after impact? We called it Vs, okay? And Vs, by definition, what do? We need to take x times beta cap plus 2 lambda times alpha cap, okay? So the component along beta is x, so it's going to be x times beta cap, okay, plus 2 lambda, because 2 lambda was a component that is perpendicular, which was y, times alpha cap. Okay, that is it. But what is x? Our x was lambda, so you are going to have lambda times, what is beta cap? This is beta cap here. So alpha times beta cap plus 2 lambda times, what is alpha cap? I think I've forgotten. Let's just take it from here. Alpha cap is this. This is alpha cap. Okay, let me simplify. So I'm just trying to be adding some equations. Okay, so there's supposed to be multiplication. If we simplify, we are going to have, in the I component, we are going to have lambda is outside. Okay, we are going to have 3 on 5 plus 8 on 5. Okay, then plus, for the j component, lambda is still outside. We are going to have 4 on 5 minus 6 on 5. Good. So now this gives us 11 on 5, so 11 over 5i. Then here we have minus 2 over 5j meters per second. There is a lambda outside, so we put a lambda. So this gives us the velocity of sphere S after impact. That's the velocity of sphere S after impact. Okay, so that's the velocity of sphere S after impact. Okay, so if they ask you for the speed, you now need to take the magnitude of the velocity. If you're being asked for the speed, you take the magnitude of the velocity, it gives you the speed. Okay, so I think what if they ask you for the angle, the angle of inclination, this alpha? I think I've already explained about alpha, because alpha is equal to 1/5, so you can find alpha. Or even from tan alpha equal to 2, you can find alpha by taking tan inverse on both sides. Okay, so let us move on to the next GCE year, which is 2017, which is going to be the last GCE year we are going to be looking at. Okay, alright, so it reads, show that the vectors 3i plus 4j and 4i minus 3j are perpendicular. Let's start with that first part. So what do we know about perpendicular vectors? So let me just write a statement. If A and B, so if A and B are perpendicular, then we know that if we do A dot B, the result is 0. Okay, A dot B must give us 0. So let's do the dot product. So our A dot B in this case gives us what? In fact, you just realize that we in the previous question, this was a vector equation, right? And then we were using this perpendicular vector after finding it. But in this question, they have actually given you the perpendicular vector, so there is no need to find it again. I think when you read the next question, you're going to actually get it. Okay, so I'm going to take a dot b to give me, what is a? 3, 4 dot, what is b? 4, negative 3. So this gives me 12 minus 12, which is 0. So hence a and b are perpendicular. Hence a and b are perpendicular. Okay, that was the first part of the equation. Now let's read the next part. A smooth sphere A of mass 2m moving on a smooth horizontal floor with velocity 10I plus 5j meters per second impinges obliquely on a smooth stationary sphere B of mass m. At the instant of collision, the line joining the centers of the spheres is parallel to the vector A given above. So it is perfectly the same problem, a similar problem we have had before. So there will be no need for us to be finding those unit vectors again and all the rest. In fact, yes, there will be no need for us to find it again, right? Because I think we found it already. Now, given that the coefficient of restitution between the spheres is E, okay, and that the direction of motion of sphere A after impact makes an angle of alpha with the line of centers of the spheres, show that this happens. Then show that tan alpha is between 3 on 4 and 3 on 2. Then given that tan alpha is 1, find the coefficient of restitution and hence find the velocities of A and B after impact. Okay, so here's the last example we are going to do. Okay, so since we have done with the first part, we have to draw the diagram. Now it is kind of a similar, so I'm just going to copy this diagram and paste. Then we change what we need to change from there. Okay, because there is no much changes between the two of them. Sorry for the error. My Microsoft Word is not responding because I think the video is the live session is already long, so it's going to come back very soon. Okay, so we have a similar diagram where we just have to change things. We have the same vector 3i plus 4j because according to the equation, at instant of collision, the line joining the centers of the spheres is parallel to the vector A. So at the instant of collision, the line joining the centers of the spheres is parallel to the vector A. So I'm going to call this component here maybe X. In fact, I'm just going to give it the same thing. Call this component Y. We are going to find all those components. No, let's call this one A. Sorry, because X is already here. Then this Y does not change. Okay, it is perfectly the same thing. But now this is sphere A, and then this is sphere B. Initially, sphere B was at rest because they say it was stationary. Stationary means you're not moving. Okay, it was stationary. Okay, now so this is VA. This final here is VA. Okay, voila. So this is what we have. Now, again, the question said yes, the angle is alpha. All right. So there's not talk about the angle made with this initial angle, though it exists. Okay, but we don't need it. But according to what the equation is saying, this final angle is alpha. Okay, this angle here is alpha. Because the equation said it clearly. It said that, and that the direction of motion of sphere A after impact. Are you seeing the word after impact? After impact makes an angle of alpha. So after impact, we are here making an angle of alpha with the line of centers of the spheres. Okay, so I think with this we have actually, so first things first, for us to even start the equation, we must find those our components. Okay, now, so what will I do? I'm just going to copy everything we have done before and just paste. Then we just change what we need to change. So yes, we are going to let all of this. I think all of these things is the same thing. What we just change is from here. Yes. So let me just copy everything here, okay, and paste it down there. We try to adjust because I cannot start retyping back everything. I think the video is already long, but you have to be persistent till the end because you have to actually understand. Okay, so let us start the analyzation process. Okay, so I'm starting. So let alpha be equal to ci plus dj be the perpendicular to, according to the equation, this is a vector a. Okay, so I'm going to call that a. Yes, no need to call this one alpha again. Let me just call it in fact it is even the vector b. In fact, there is no need to even find because you have already realized that the vector a is perpendicular to the vector b. Okay, so there is no need to do that stuff again. So unit vector in the direction of the vector a, this is my vector a. The unit vector in the direction of the vector b, this is my vector b. Okay, the same answer because it is practically the same vector. So practically the same story. Now initial component of UA, because this first now UA in the direction of the vector A, it is same. Now what is UA? Voila, UA has now changed. Here's a unit vector of A. Here is supposed to be A. Okay, then just try to change everything from beta to A. Then for B, this is B, this is B, and this is B. Good. So let me just change this man to UA, and then this is B, and then this is UA, and then this is B. Good. Okay, so this man and this man are not changing. What will change is just this man. So let's go to UA. What is UA? 10i plus 5j. So you are going to have here 10, you are going to have here 5. Okay, 10 and 5, 10 and 5, that's what we have. So if you do that, in the place of 4 lambda, we'll just have to replace 10. I think you are actually supposed to do this by yourself. Okay, then here we have to replace 5. Then here we replace 5. Now let's simplify the first one. There is no lambda, there's no lambda anything. So you are going to have here 10 plus 10, 30 plus 20, 50 over 5 is 10. So we have 10. Here we have 40 minus 15. 40 minus 15 is 25, 25 on 20, 25 on 5 is 5. So that's what we have. Good. Okay. Wait. Did I copy 2 diagrams? What's this diagram doing here? Wait. What's this diagram doing here? Wait, let me check if the diagram is still okay. Savannah. Okay, so I think for this stage, right, you yourself, you have to do it by yourself. Try to follow up the previous explanation and do it. But what is nice is that we have already gotten our components. So this A is 10 and this Y is 5. So I'll come back to the diagram, replace A with 10, okay, replace Y with 5. So I'll also replace Y with 5. Good. So I'm left to find X and VB. That is what I'm left to find. Okay, so let's now start analyzing the equation. So this says that we have to show, yes, the equation starts by saying that show that we have 2 things to show first of all. So let's start from here, which is saying show that. So let's start by showing this. Okay, so what we are going to do is we are going to apply our Newton's law of restitution and the law of conservation of linear momentum along the line of centers. So I think we'll also need to carry this diagram down so that we use the diagram to solve. So I'm going to take the diagram downwards so that we use the diagram. Okay, so I think we can just put the diagram here. Yes, you can put the diagram here. Good. Okay, so we are going to apply Newton's the principle of conservation of linear momentum. So we're going to apply this principle, and then later we apply Newton's law of restitution along the line joining the centers of the spheres. So first things first. Okay, let us apply the principle of conservation of linear momentum. It says momentum before collision equals to momentum after collision. Before collision, we have, what's the mass of A? 2m. the mass of B, M. Okay, let's go. So we are going to have 2m so we are going to have 2m. We multiply it with the initial component of the velocity of A in the direction along the line of centers, which is 10. So we have 10 plus the mass of B is m. It was stationary, so we have 0 equal to 2m times x. Okay, because that's a final velocity of A in the direction along the line of centers, plus m times VB. Good. So from here, all the m cancels. The left hand side is 20, the right hand side is 2x plus VB. So this is equation 1. Now let us go to Newton's law of restitution. It says that the coefficient of restitution E in this question is E, that's not been given to us. It's equal to velocity of separation. So we are going to take VB minus x. Okay, I think that's it. Okay, because we have VB minus x equal to 10 minus 0. Yes, because we are not starting with u. We are not starting with UA. So we have 10 minus 0. So this means that if I multiply all by 10, I'm going to have 10e is equal to VB minus x. That is equation 2. So we are going to solve these two equations simultaneously. Okay, we solve these two equations simultaneously to get VB and x. So we start by taking equation 1. If you take equation 1 minus equation 2, realize that the left hand side will be 20 minus 10e equal to 2x minus x is 3x, then VB minus VB is 0. So what will be x? The result will be in terms of e. Okay, so my x will be equal to, now 20 and 10 is common, so we have 10 into 2 minus e divided by 3. So this is my x. Now let us find VB. So to get VB from equation 2, we realize that VB is just equal to 10e plus x. So we're going to have 10e plus, what is x? There's a 3 down here. I'll just put there 20 minus 10e. Okay, so the LCM is 3. We are going to have here 30e, because 30e on 3 is 10e, then plus 20 minus 10e. So in essence, we can conclude that VB is equal to, the LCM is 3. Up here we have 30e minus 10e is 20e, then plus 20. Now since 20 is common, we have 20 on 3 into e plus 1. Okay, so I'm just trying to write it in the most simplified form. Okay, in the most simplified form. So for this one, we could write, I think we could write 10 over 3 into 2 minus a. Yes, it is better this way. Okay, so we have found VB and we have found x. Good. Now let us go to proving that 4 minus 2e tan alpha is equal to 3. Now alpha is the angle of inclination after impact that VA makes with the line joining the centers of the spheres. And by definition, if we took tan alpha, we are going to have opposite, which is 5, over adjacent, which is x. Okay, so let's go. Tan alpha is opposite, which is 5, over adjacent, which is x. So this is going to give us 5 over, what is x? This is x here. Okay, so here is x. Now what happens is that the 3 moves up. Okay, 3 moves up and meets 5 to become 15. Then we divide it by 10 into 2 minus e. So from here, what do we have? I think 5 can go up here 3 times and can go here 2 times. Okay, so we are going to have tan alpha to be equal to 5 going there 3 times, going here 2 times. The 2 we multiply with 2 to have 4 and multiply with e to have 2e. Then we now cross multiply. Once we cross multiply, we have 4 minus 2e times tan alpha equal to 3. I think here is a proof, right? So we are proving that 4 minus tan alpha is equal to 3. So we have successfully gotten the first proof. Now let's move to the second proof. So in the second proof, we are going to use the idea that the coefficient of restitution E is always between 0 and 1. Okay, this is the idea we are going to use, that E always lies between 0 and 1. Then I think from there, since we know that tan alpha is equal to everything here, okay, we are going to try to bound what is here. So I'll start by looking for where is negative 2e lying. So I'm going to multiply all through by negative 2. Once I do that, inequality sign reverses or the bounds can change. So I'm going to have negative 2 less than or equal to negative 2e less than or equal to 0. Because once I multiply, I'm going to, here was normally supposed to be negative 2, but it's going to go to the lower bound because the inequality, if it's negative 2 here, then this inequality sign will change to greater than. And if negative 2e is greater than or equal to negative 2, it means that negative 2 is less than or equal to negative 2e. So this is what we have. The next thing to do is that we add 4 on all the sides. If we add 4 on all the sides, here we are going to have 4 minus 2 less than or equal to 4 minus 2e less than or equal to 4 plus 0. Okay. Now let us simplify. 2 here less than or equal to 4 minus 2e less than or equal to 4. Now we need to make it to be in the denominator. Okay, we have to make it to be in the denominator. So we are going to take the reciprocal on all the sides. And when we take the reciprocal, we need to interchange the position of the upper and lower bound. So here it's going to be 1 on 4 less than or equal to 1 over 4 minus 2e less than or equal to 1 over 2. Okay, we're doing that because I cannot allow this as 1 over 4, because 1 over 4 is 0.75, sorry, 0.25. Then 1 over 2 is 0.5, but we know that 0.5 is bigger than 0.25, so we cannot put 0.25 up here and 0.5 down here. Okay, the next thing is we will multiply all through by 3. So once I multiply all through by 3, I'll just have 3 here, I'm going to have 3 here, and I'm going to have 3 here. We realize that the middle term is tan alpha, perfectly tan alpha. Okay, so we can conclude that therefore 3 over 4 is less than or equal to tan alpha less than or equal to 3 over 2, and we have proven. Now, given that tan alpha is equal to 1, find E. So if tan alpha is equal to 1, we know that normally tan alpha equal to 1 means that our tan alpha is everything here, okay? So it means that everything here is equal to 1. So if you, or you can just come and replace 1 here. Yes, there's no problem. So if you cross multiply, you are going to have 3 is equal to 4 minus 2e. Then from there we subtract 4 on both sides. We have negative 1 is equal to negative 2e. Then we now have to divide both sides by 2, and e is going to give us half. Now hence, find the velocities of A and B after impact. So I am going to find the velocity of A, then you will find the velocity of B. So the velocity of A after impact, VA, from the definition, what do we need to take? We need to take x and multiply with the unit vector along A plus 5 multiply with the unit vector perpendicular to A. Okay, so we are going to have x, we take x, okay, we multiply with A cap, the unit vector along the line of centers was A, okay, then plus that perpendicular component was just 5, then we multiply it with the unit vector perpendicular to that, which is B. So this is going to give me, what was the value of x? I think x was 10, right? So we have 10. What is A cap? Just come back and copy. So my A cap is this, okay, and just take alongside with this man so that we don't have to come back again. So this is A cap, this is a cap, then plus 5 times this is b cap. Okay, so let us simplify. So you're going to have 10 times 3, 30 over 5 plus 20 over 5, that is 50 over 5, which is 10. So we have 10i. Oh, wait. What is our x? What is x? This x is gone. X is 10 over 3 into 2 minus e. But e is half, so let us find x. Sorry about that. This is actually x is actually 10. Okay, let us find x. X is equal to 10 over 3 into 2 minus half, because e is half. So we have 10 over 3 into 2 minus half is taken on 2. So you're going to have 5 as your answer. So this one is supposed to be 5. Okay. Then your perpendicular component does not change after impact, so it is still 5. So this is going to give me 5 times 3, 15, plus 5 times 4, 20. 15 plus 20 is 35. 35 on 5 is 7. So here is 7i. Now 5 times 4 is 20 minus 15. Okay, that's 5. 5 on 5 is 1. So plus j. So this is the velocity of the sphere A after impact. You can now find the velocity of sphere B after impact. Okay guys, thank you for staying till the end. That's been a very long session, but I believe you guys are really picking up with the explanations. In the next session, we are going to solve more GC equations. For your assignment, you can now check June 2020 assignment. Assignment is June 2020. Paper 3. I don't know the equation, but I think when you read, you are going to identify the equation. So this is your assignment for today. So here is my contacts. You can get to me. I'm going to add you to the further maths revision group, where I'm going to send some more questions on this topic. Okay, so it has been a very long session, like I said, and I'm extremely tired. See you guys in the next live session. Without wasting much of your time, good night.